Okay, so welcome to this module of thermochemistry. Going ahead, so enthalpy of formation and bond energy. So from enthalpy of formation we can get an idea that how much strength is there in a bond formation. Just now we have seen, right, one example of CO2, it was almost 1600 we got, right. Is it now we can get a sense of number from many other things. So let us say we are talking about AB formation from A and B. Now looking at the enthalpy of formation of AB, if the A and B are in standard states, then we will get the bond energy of AB. So for example H2 is forming from 2 Hg, like 2 hydrogen atom, and enthalpy of formation is typically 2 into 2 and 7, so giving rise to 435.998 kilojoule per mole. So that is the formation of hydrogen molecule from hydrogen atom, or rather it is getting stabilized. So it is the other way around, we have written the equation from H2 to 2H, which is, that means this much energy has to be supplied. But remember this is at 298, that is not the bond energy, that is at a finite temperature. For bond energy you have to calculate the value at 0 Kelvin, that is the intrinsic bond energy, right. So how do you calculate the 0 Kelvin, we will come back to that, but before that I will give you some more numbers which will give you an idea. For example NH is 391, it is actually smaller than H2, and the reason is that it is a heteroatomic system. So electron is more towards nitrogen. Look at carbon 348, and C triple bond C 839. So we knew, right, that double bond triple bond is more stable than the double bond, and double bond is more stable than the single bond and all that. See nitrogen triple bond very strong, you see, triple bond nitrogen, most stable compound, one of the most stable compounds, and that has like 945 kilojoule per mole strength, and this data I have got from this site here mentioned. So idea is that from heat of formation you can get that, but only when they are very simple molecules, like a diatomic molecule we are talking about. Okay, so you see that for complicated molecules this bond energy calculation will be very difficult. For example, we can let us say if I talk about CHCl3, let us say CHCl2 plus Cl. Now this kind of processes, if you see, or let us say CH2Cl2, you are going to CCl4. So we have to understand that all other connectivity that are there. So we cannot calculate the CH bond strength by this, because there are other residues, substituents involved in this process, right. So it is very difficult to get only the CH bond energy by heat of formation method. Similarly, sometimes there are more than one conformation are possible. For example, methyl cyclohexane. Methyl cyclohexane can be there in both axial and equatorial position, right. So in that case they will have different heat of formation, and we are only going to get an average value. So therefore the quantum calculations are helpful, which can give you from ab initio method these bond energies. So we have studied the energy of hydrogen atom, right. Similarly we can study energy of hydrogen molecule, we also studied hydrogen molecule, right, bonding energies, and the bonding values of hydrogen molecule is pretty close to our calculation, we will talk about that. So you see 435.998 is at 298 Kelvin, right, at 0 Kelvin it is around 432, which is very close to the quantum chemical calculations. Okay. So quantum mechanics can give you an idea about this bond strength, which can be experimentally verifiable using this kind of systems. Now how do you get enthalpy at different temperature? So in order to understand that we have to see that standard enthalpies are defined only for 1 bar pressure, but it can be at any different temperature, right. So standard enthalpy of many reactions can be calculated at different temperatures. However, if this information is not available, it can be obtained from heat capacities. How? Let us say we already know that delta H or dH is Cp dt. So which means that by integrating this particular quantity we are going to get the enthalpy at a different temperature. right. For any system we can heat it up, and depending on its own heat capacity we are going to get the change in enthalpy from one temperature to another temperature. So, it is like this. You imagine that we are talking about a reactant, and that reactant has different values at different temperature, right, and this is a product which also has different enthalpy at different temperature. Now, what we are observing at one temperature like this and another temperature like this will be only different by their difference in Cp's. So, if I now take the difference in Cp's, then we can get the difference in enthalpies at two different temperature, you see. So, and that is what it is mentioned here, which is called Kirchhoff's law. So, reaction at one temperature T2 is equal to reaction at heat of reactions at one particular temperature T2 is equal to heat of formation at a particular temperature T1 plus integration of T1 to T2 delta R Cp. So, it is now the difference in the reactions of Cp, which means that the same way we calculate reaction enthalpy, we are calculating the reaction Cp, okay. And that the reason is graphically shown here, and once we do that we are going to use that delta Cp to calculate the process. And again we can write in general delta R Cp as the stoichiometric. So, Cp's difference in Cp's multiplied by their stoichiometric coefficient, just like we did for reaction enthalpy, same thing, but for Cp. Once we get the Cp, we multiply by the temperature and add the enthalpy of one value. So, also it will be clear here, you see here we know the value of heat of formation or heat of formation of a hydrogen atom from hydrogen molecule at 298 Kelvin, okay. And we also know the heat capacities of hydrogen gas from. So, we can calculate the enthalpy change from 0 Kelvin to 298 Kelvin, we can calculate that. Similarly, we can calculate this by knowing the heat capacity of hydrogen atom, we can calculate the difference in heat from 298 Kelvin to 0 Kelvin. Now, having those all these three values, we can calculate the change in enthalpy at 0 Kelvin. It is called thermodynamic cycle. So, cycle means there is a cyclic step out of which you do not know only one value, you know all the other three. From all other three we can actually calculate the last one. So, it is using exactly this thing. So, we know this point, we know this point, I will use a different color. We know this point, we know this point, we know this point, we have to know only that. We know this step, we know this step, we know this step. So, we can calculate that 1, 2, 3, these 3 we know, only thing we are calculating is the last one, this one. Now, this is just a simple example that standard enthalpy of formation of a gaseous H2O at 298 is this much value, estimated its value at 100 degree centigrade. Okay. So, 298 Kelvin and 100 degree is 373 Kelvin, right. So, molar heat capacities of water, hydrogen and oxygen are given. Assume the heat capacities are independent of temperature, that we have to, otherwise we cannot subtract them because they are going to change, right. So, that formula is very clearly here. So, first we write down the reaction H2 plus O2 is H2O, then we calculate the delta RCP, that means reaction heat capacity. So, which is given by terms in their with the coefficient as the stoichiometric values, and that is giving us a delta RCP as minus 9.92. Now, how much change in temperature is there from 298 to 373, that is will be 75 degree. So, 75 multiplied by 9.92 and add the value whatever was there as 241.82. Once we do that, we get minus 242.6 kilojoule. So, that is how knowing the heat of formation or heat of reaction at one temperature, we can calculate that in other temperatures, and like that we can also we can now calculate heat of formations for all possible systems, for reactions, for physical changes, for biochemical reactions, and also by knowing that we have a sense of the internal energy of a particular system. And remember that once we understand the internal energy of a particular system that is stored, we can get an understanding that which can give us heat and therefore, which you can use for work. That is why we are storing methane, right. People are nowadays trying to store methane. Why? Because methane can give us energy, water it cannot, but water is more stable, but hydrogen is less stable, which means hydrogen has more internal energy which can be extracted. So, that is why people are trying to split water into hydrogen and oxygen, so that hydrogen can be used as a fuel. See, so basically somehow the energy that is there, if you can use that and store it just like a battery. So, if you can store methane, then it will be used as a source like a battery in future, right. So, similar so the all ideas of doing that is that, so and these are we call as chemical energy that we are storing. For example, food gives us the energy, right, glucose, because it is not as stable as carbon dioxide and water, it can be decomposed into that and giving us the energy. If it would be very stable, we cannot extract any energy out of that, it can only go lower spontaneously. Okay. So, that is why it is very important, and this kind of ends the first law of thermodynamics.